Hi, class. So today we're going to talk about the history of life on Earth. We want to understand how life has developed and changed over time. That will give us clues for things we should look for, ways that we could look for life elsewhere. So this is setting the stage for next week. We're going to start talking about moving off of Earth into the solar system to start with and talk about looking for life there. So behind me today, you can see here a fossil picture of what are called trilobites. We're going to talk about fossils a lot, but I wanted to show you. Trilobites are my favorite fossils, so I have some of mine here to show you. So this is, I don't know if you can see it there, right? So this is a very kind of typical little trilobite. You can get these in Evanston if you go down to Dave's Rock Shop once everything's back open again. You can get little trilobites like this. At a museum store, you can often find really nicely processed trilobites. So you can see that one. That one's been polished and cleaned up, and it's still in the matrix of the rock that it came in. Okay, so that's kind of what the trilobites look like. You can also find other fossils. So this is another kind of very common one you get. This is called an ammonite. Okay, so ammonites are greatly prized by people because they have kind of iridescent colors in them, which you probably can't see in the light that I'm filming in here. And of course, you can see things like this. So this is petrified wood, which many of you have probably seen. So you can see there, that looks just like the cross-section of a piece of wood if you went out in your backyard and cut a cross-section through a tree. Okay, and so the fact that you can look at things like this and recognize their structures as being similar to things that you see when you look around you in the world at life forms that are alive today is one of the things that we use when we look for the records of life in the history of the Earth. Okay, so keep that in mind. But let's go through this bit of the lecture. So I am going to start a couple slides here. Okay, so we're going to talk about the record of life on Earth. There's another trilobite fossil. Trilos are my favorite, as you'll find out. So the first thing I want to do is I want to talk about the oldest living things on Earth. If we're going to talk about life, we should certainly talk about what we know about life as it exists today, beyond just you and I. And then we're going to look about the history of life. So we certainly want to know about the oldest things that might exist. We'll talk about fossils and the record of life that exists in the rocks and a little bit about what we understand about it. And then we'll talk about signatures for life that we'll actually look for in the geo record of the Earth. Now, I should say that all of these topics are things that we could talk about at great length for an hour or more. So we're just going to gloss over this. We're going to talk about the very high points of this. Your book does the same thing. We're reading in chapter 6 right now. So we certainly aren't going to talk about every little detail that we could possibly talk about. If you're interested in this and you start reading about this, there is a long and very well-developed record of information that you can find in books and on the internet. Okay? So the history of life on Earth, as you might guess, or as we will discuss, is very extensive. And what we mean by extensive is it extends very far back in time. This is actually one of the things that is most interesting about the development of life on Earth, is that, as we will see, it started very soon after the Earth itself formed. It's also remarkably diverse, and we don't necessarily know why that is. We understand how it becomes more diverse once the diversification of life starts. But one of the interesting questions is, why did it become diverse to start with? Okay, so if we look at all of that history, we look at how long it is and how diverse it is, that's the kind of information we're looking for that's going to provide insight for us when we start looking for life on other worlds. And what I mean by providing insight for us is framing it in that context that we've already talked about, which is the principle of mediocrity or the rare earth hypothesis. All the things that we talk about are things that you should be able to look at and think about and turn around in your head, and then go back to these two principles and ask yourself whether or not the things that we see here on Earth convince you that the Earth is quite ordinary and the things happen on Earth might happen everywhere, or whether or not the things we happen on Earth are quite extraordinary and it's probably not likely to happen elsewhere in the cosmos. You can always take all of these little bits of information and kind of imagine which one of these two blocks you could pile it on top of. Okay? Okay, so let's talk about the oldest things on Earth to start with. So there is an absolutely fantastic book that you can get. It's a coffee table book, and they probably have it at the library if you go look. It's by Rachel Sussman, and what she did is she went around the world and she photographed all the oldest things that she could find, the oldest living organisms on the Earth. And there are some truly ancient and very old organisms on the Earth. So this is just a selection of the things that she talks about in her book. You can certainly find many other old things, which I'm not going to talk about. But it's interesting and useful to talk about how old organisms are, because when you start talking about the existence of life and the persistence of life, in some sense, life is really measured by how long a single individual persists and whether or not that life form is able to propagate itself into a new individual. Okay, and these are all organisms that have persisted for very long periods of time, and as it turns out, there are other examples of them throughout the world. These are successful organisms that are existing and surviving in a harsh universe. This one here on the upper left is called the Pando Forest. It's a single aspen grove. So aspens are a form of poplar tree. They are colonial. That is to say that they're all one single organism that grows out of a common root ball, basically. So when aspen grow, they send out runner roots and it sends up a new sapling. So this grove is something like 100 acres across, and it's been there for 80,000 years. Okay, so it's in the Fish Lake area of central Utah. There's a nice campground there. You can go sleep with Pando and sleep with one of the oldest forests on the planet. Over here on the right, on the top right, is what's called the seagrass meadow. This is called Neptune grass. It's in the Mediterranean there by the Balearic Islands in Spain. And this bed of seagrass is 100,000 years old. Okay, so this is super old. Now, life began in the oceans, and so it's really intriguing to find old life forms living in the oceans. Down here in the lower left is a moss colony from Elephant Island in Antarctica. So Antarctica, as you know, is a very harsh environment. The ecosystem there is very niche. And so there are lots of organisms that exist and they survive. They don't have a lot of competition. They don't have a lot of predators. There's all kinds of interesting biology to study in Antarctica. But this Antarctic moss on Elephant Island is 5,500 years old. Okay? And then lastly, over here on the lower right is some actinobacteria. This is from the permafrost in Siberia. And so this has been living in the permafrost for 400,000 years. It's not frozen. There certainly are bacteria that do freeze. This bacteria has adapted, and it goes through its normal metabolic activities in the permafrost, but at a much reduced rate. Okay, so these are all examples of life forms that have existed for very long periods of time. And you can imagine if they are propagating individuals, the way you and I are propagating individuals, you could take one of these lifetimes and propagate it backwards and see how many generations of such life forms existed since they first appeared on planet Earth. Okay? But most life forms don't live this long. Humans live kind of 100-ish years. Our pets live kind of 20-ish years. Your goldfish lives a couple years. Not all life forms have these great extended lifetimes that we're talking about here. So if we want to talk about the history of life on Earth, if we want to understand the history of life on Earth, then we have to be able to understand what the record of all the life that has perished is, all the life that came before today. Okay. Now, organics decay over time. That's part of the natural life cycle. We've talked about how life forms prey on each other for raw materials, and part of the balance of the ecosystems is when you and I die, it's lunchtime for the bacteria, and the decomposition of organic materials is the bacteria using us as raw materials for their own life processes. Okay, so since organics decay away, that means there are no organics today from long, long ago. And so the only thing we can find on Earth from long, long ago are rocks. So our only hope for looking for the record of life from long ago is to look for records of the life in the rocks. Okay, so there's basically three ways you can imagine doing that. One of the ways is you could look for structures, for fossils, just like the trilos that I was showing you right there at the beginning. Okay, so we look for things that look like life, but they have turned into rock, and those are what we call fossils. And we'll talk about that in a minute. We can also look for evidence of chemistry. So basically, life goes through processes which deposits compounds associated with their life processes, and those concentrations of compounds could also be concentrated in the rocks. Chemistry is a little difficult way to look for life. We do certainly do it, but one of the things is it's often easy to be fooled because there are geochemical processes that have nothing to do with life, which can fool us sometimes and look like the chemistry of life concentrating materials in the record in rocks, okay? And then lastly, there are isotopic searches we can do. So isotopes are basically different forms of specific atoms on the periodic table. And if you look at the atoms that life uses, life often prefers certain isotopes of certain atoms. And so we're in places where life has been plentiful, those isotopes are concentrated in the ratios that life favors. And so we can certainly look in the rocks for isotopic asymmetries that look like life was doing its business there before it became trapped in the rocks. Okay, so we'll come back and we'll talk about each one of those things here in turn. So let's start with fossils. So I showed you a whole bunch of fossils at the beginning from my collection here in my study. You can certainly see plenty of fossils if you go to museums. Some of you may have fossils at home. These are very common and typical ones. Fish, you can certainly find. Lots of people have fish fossils, and there's plenty of fish fossils that are very, very nice, just like this one, because the oceans laid down sedimentary layers that trapped dead fish over many millions of years. These kinds of fern fossils, like you see in the upper right here, these are also very common. They're found in shale deposits all over the world. There are many places where you can go dig into shale deposits and find your own fern recovery fossils. There's another trilo, of course. And for those of you who have been down to the Field Museum here in Chicago, that is our own resident fossil. That is Sue the T-Rex. She is probably the most famous T-Rex skeleton in the world, okay? But she's on display at the Field Museum if you want to go see her. So fossils result because when organic material is deposited, when an animal dies, if it isn't exposed to the natural ecosystem where the bacteria and the scavengers and all the other life forms are going to prey on it and break it down, if it's, for instance, buried in mud or covered up somehow where the bacteria can't get the oxygen they need to do their job, then the organic material can be preserved. And particularly when it's covered in mud and rocks and things like this, mineralization occurs. So the natural geochemical processes, there are reactions with the organics that the life form is made of, and you take what used to be organic tissue, bone, soft tissues, whatever, and you replace it with minerals. And those minerals harden and solidify into rock, basically. And that rock is the materials that our fossils are made of when we find them. So the job of uncovering fossils is really digging into the rocks and sloughing off the rock that isn't part of the fossil, recognizing pieces that are, and keeping them so that you can discover what the function and form and shape and size and all the properties of ancient life forms may have been. Okay? Now, we've been talking a lot about micro life forms, single cellular life, When we look at the tree of life, two entire branches are single cell branches, the bacteria and the archaea. It's only along the eukaryotic line that we have multicellular organisms. And so if we want to talk about the history of life, and indeed we want to talk about most of the life on the tree of life on Earth, we have to somehow talk about the history of single cell organisms. And so it's natural to ask is, does small life fossilize? And the answer appears to be yes. And so what we do is we look in the stratigraphy, in the rock, for things that look like bacteria. And so up here on the top, there are a couple examples of candidates that we think are fossils of cyanobacteria. Okay, and we're going to talk about cyanobacteria a little bit more. Okay, so they clearly are very tiny. They have cellular-like structure to them. And so the real question, whenever we find something like this, is, are there geochemical processes that can make something that looks like basically the fossil remnant of a bacteria? So in particular, I'll point to this one over here on the right, right? Those center cells there look pretty square. Okay, so you might say, well, are there geochemical processes that can produce things that look pretty square? Well, the answer to that, of course, is yes, because there are lots of minerals that have nice cubic structure. A good example is salt. Okay, so it's very dodgy some days trying to convince ourselves that such things as this are indeed microfossils, but we can gain confidence by often combining it with one of the other techniques, with isotopic analysis or with chemical analysis. Okay, and we'll come back to that in a minute. On the bottom there, these are much larger structures. So these are kind of microns across. So these are the fossil remnants of multicellular or much bigger cellular type organisms. And so we certainly find plenty of very remarkable structure that is very similar to the structures we see in modern microscopic life forms. And they certainly do fossilize just the way big things like Suga T-Rex does. Okay? Now, there is other good evidence for fossil bacteria, okay, in the form of what we call stromatolites. So stromatolites are bacterial colonies. So basically, bacterial colonies grow in these large mats, particularly in water areas. Those mats build up over time, and the top of the mat is, in the case of cyanobacteria, typically photosynthesizing. Okay, so over here on the left, this picture is of living stromatolites in Australia. Something I learned when I was writing this lecture, I've known about stromatolites for a long time, but I didn't realize we didn't know about them until 1956. So it was only in 1956 that the first stromatolites were discovered in Australia. So that's within the lifetime of my and your relatives, although not in my and your lifetime. Okay. On the right there, that is a fossilized stromatolite. So you can see the very deep layering that you see there. That is the mats building up one after the other as the bacteria grow in their colony. And then when that colony, that stromatolite, becomes fossilized, it leaves that record of the layers of mat growth in the rock. And so you can see that striation clearly there across that. Now, the oldest known stromatolite fossil that we know of dates to about 3.48 billion years. So that is a stromatolite fossil from Australia. It is uncontested that it is a stromatolite. It has microstructures that look like the algae. It has isotopic signatures. It has chemical signatures. It has this layering. It's very clearly a fossilized stromatolite. Now, there are older samples. So in particular, there's been a sample found in Greenland from a little bit longer ago, from about 3.7 billion years. There are some arguments about whether or not that is a stromatolite, because we don't have all the pieces of evidence all pointing at it, but it sure looks like a stromatolite. And so it almost certainly is true there are older stromatolites than the one that we found, but this is currently the oldest number, 3.48 billion. Okay? Now, One of the things that we talk about is the fact that life concentrates chemicals associated with its lifey processes. Okay, and so we see that kind of chemical deposition, and we see it contained in the rocks all over the place in many different forms. But the most common form is for something called carrigans. So carrigans are very high in carbon. And so life forms like you and I are carbon-based, and so we produce heavy amounts of carbon associated with our bodies, and then when we're deposited in the rocks, that carbon can concentrate itself. And so carrigan is a very broad class of materials. There's no specific formula for carrigan, but the most common carrigens you know are coal and oil. Okay, so there's a picture of a coal band there. That is all rock, right? It's coal, but it is a fossil rock. It is carrigans. It is the carbon-rich concentration of life forms that were dead and buried and compressed and transformed geologically over long periods of time. Okay, so that's an example of the chemical concentration. The isotopic concentration, largely we lean on carbon. Now, some of you may be familiar with carbon-14 dating. That's a different isotope of carbon. Here we're going to talk about carbon-12 and carbon-13. Carbon dating with radioisotopes of carbon, carbon-14, is good only back to kind of 50-ish, 70-ish thousand years. Beyond that, most of the carbon-14 is decayed away. You can't use it to tell the age of anything the carbon's been deposited in. Okay, but carbon-12 and carbon-13 are both stable isotopes of carbon. So what's an isotope of carbon? So carbon is an atom which has 6 protons in its nucleus. Okay, and each isotope of carbon, when you give the number, okay, so carbon-12, you subtract the number of protons, 6, from the isotope number of the carbon, 12, and it tells you how many neutrons there are. So carbon has 6 protons, so carbon-12 minus 6 is 6. So carbon-12 has 6 neutrons. Carbon-13 is still carbon and has 6 protons, but I subtract 6 from 13 and I get 7. So there's 7 neutrons. So the only difference between carbon-12 and carbon-13 is one has 6 neutrons and one has 7 neutrons. Okay? Now, carbon-14 has 8 neutrons, and that makes it radioactive. So after, I think the half-life of carbon-14 is something like 5,000 years, okay? So carbon-14 will slowly decay because of the extra neutron, but carbon-13 has one less neutron than carbon-14, and it's stable, okay? Now life, when it's doing its lifey stuff, it's gathering raw materials, it's gathering carbon, and building copies of itself, doing all the things that it needs to do, and it preferentially keeps the lighter carbon. Okay, so all the processing of carbon, when it's breaking up raw materials, if it can tell the difference between the heavy one and the light one, it preferentially keeps the light one. Okay, it still keeps carbon-13, it still uses carbon-13, but the amount of carbon-12 in a life form slowly builds up over time so that there's more of it than there is carbon-13. And so what we do is we can tell that something has isotopic abundances associated with life if we see an excess in carbon-12 over 13 in a deposit compared to the environment around it. So a classic example of this is limestone. So you can see limestone here. Limestone is a carbonaceous deposit. It's calcium carbonate. You can make limestone from diatoms and seashells and stuff like this. Okay, those are all formed from life processes. Okay, and so if I have limestone that was formed from life processes, then it has an excess of carbon-12 over other rocks that I might find in the same area. Okay. So that's the way we use isotopic searches. So it's all of those things together. It is the search for things that look like life. Sometimes it's easy to tell that it looks like a life, like in the case of a trilobite or the case of a piece of petrified wood. Sometimes, like with the case of microfossils or microscopic bacteria, it's not so easy. And so then we have to lean on those other techniques that we have, the chemistry and the isotopic abundances. Okay? Okay, so that's all I'm going to say for this lecture. We'll come back and we'll talk a little bit about the history of life over Earth, over Earth's history for the next half of the lecture, and then we'll be ready to talk about leaping out into the cosmos very soon. Okay, so hope you're all having a good day. I will talk to you soon.